Hi everyone. If you recall, I told you, I think at the very first um, video, that this course is meant to be able to be taken without having had a Calc 2 or Calc 3 background. And this is the first time today that we cover some material which assumes you've had a Calc 2 background. So before I get into it, let's do just a little quick background work and something that you're going to need to know in order to be able to understand this section. So, we're going to be getting into the population model again, which is where we're heading. But before we get into that, let's just do a little brush-up work. So let me just start with this. Simple enough. We're going to take 5 over x minus 1 and then subtract 3 over x plus 4. Okay? Suppose you're in an algebra class and you're asked to make that, to simplify that. And the way to simplify it is to put it under a common denominator. So of course the common denominator is the product of these two things. So I would have to multiply this by an x plus 4 over an x plus 4. And I'd have to multiply this by an x minus 1 over an x minus 1. Agreed? Now I have a common denominator. So once I have that, then I'm going to have, I'm doing several steps in one here. I'm going to get 5x plus 20. And then subtract, here I'm going to get a 3x minus 1. Or I should say 3x minus 3. Agreed? 3x minus 3, and all of that is over the denominator, x plus 4 times x minus 1. And then finally, you can do a little simplification here. You get 5x minus 3x is 2x. And then 20 minus a negative 3 is going to be 20 plus 3. It's going to be 23. All over x plus 4 times x minus 1. Okay? So that is something that you have already done, right? I assume you've done that in algebra. And what I'm going to show you now is going in the reverse direction, okay? If you have two fractions like this, you can write it as a common fraction like this. The question is, what if you are given something of this form? How can you end up writing it as 5 over x minus 1 minus 3 over x plus 4. How can you take this and go back in this direction and write it like that, okay? And the reason why we want to do it is that if you have yourself a integral of this form, something like this, that you want to integrate, then how do you do it? The way you do it is to go backwards and write it like this, dx, dx, and then with each of these you can do the logarithm and you get it, see? So that's why we're heading in this direction, because you want to take something like this and want to be able to go in this direction with it. So these are things that you typically learn in a Calc 2 course, but I'm assuming you haven't had that, so we're going to give you a quick background in it now. So let's do an example just to show how you go in that other direction. So suppose you have, let's take the same one that we had, 2x plus 23, that was what we got for an answer, all over the quantity x minus 1 times x plus 4. And how do we go about doing it going backwards? And the way we do is we say, well, this can be written as something over x minus 1 plus something else all over x plus 4. We know it can, because if you started with this, you'd be able to do exactly what I did just a minute ago and go backwards and put it in this form. So we know that we can take something like this and write it as some constant over this and some constant like this. It's just a matter of finding what those constants are. So, so the first step is to take something like this and just write it as a over this first thing, and then some other constant b over this thing. And then we just have to find the a and the b. And the way we do it is we just multiply through by the whole denominator. So we're going to get 2x plus 23 is equal to, if you multiply through by the denominator, then this will cancel with this. I'm going to get a times the quantity x plus 4 plus b. When you multiply through by the denominator, those two will cancel. I'm going to get b times the quantity x minus 1. Agreed? So you're going to get that. So now, whatever a and b are, they have to be true for all values of x. So the easiest way to do it is to be judicious in our choice of x. And in particular, if we let x be equal to 1, I should have given myself a little more space over here. If x is equal to 1, then what happens to both sides? If x is equal to 1, I'm going to get 1 times 2 is 2, plus 23 is 25 on this side. And the reason I chose x is equal to 1 is because now that goes away, and I just have 1 plus 4 is 5 is going to be equal to 5a. See that? And then right away from that, we can get a is equal to 5. Now, how do we find b? What's the other judicious choice of x? Do you agree if we let x be equal to negative 4? It should work. Let's do it. Negative 4 times 2 is negative 8. Negative 8 plus 23 is positive 15. And on this side, if x is negative 4, this all goes away. Negative 4 minus 1 is a negative 5, so it's going to be negative 5b. Negative 5b, and you divide through by your negative 5, and you get b is equal to negative 3. So, boom, there we got, put a negative right there. We got what we had started with in the previous example. And as I say, why do we want to do this? Because if we want to integrate that, we can just write it like this, and then we can find the antiderivative of each of those. Okay, so that's called partial fractions. You see why? Because you break it up into fractions, into fractions which add up to this thing. Okay, so that's what I wanted to start with, just by way of a little preliminary work, just in time calculus 2 in order to do this. So now let's go back to our model for population. Recall what we had. We had this bacteria, or I guess it was mold, in a dish, and we started off with it at a certain time, and we said at time equal to 0, it was, I don't care, there were 5 grams there, and at time equal to 3, there were 12. And so given that, we wanted to find the total amount, and what we assumed was that if y of t is the amount at time t, then we said, okay, the amount of change is going to be proportional to how much is there, right? If you have twice as much there, you're going to get twice as much growth, and that gave rise to a solution of the form a times e to the kt, and of course that gives rise to a exponential growth like that. So we've done that a bunch of times now. Here's the question: what's wrong with that model? Okay, that model makes certain predictions, and one way to check the kind of the validity of a model, the usefulness of a model, is by looking at long-term behavior. What if you looked at the long-term behavior of this one? What would it tell you is going to be true for the amount of mold in that dish? And if you look at it, it's pretty obvious. The amount of mold is going to go off to infinity, right? It's going to fill the dish, it's going to fill the house, it's going to fill the earth, it's going to fill the solar system and the galaxy, and go off and fill the universe. As I mentioned in the book, there was a story once I saw of Dr. Seuss where this little boy feeds his pet goldfish too much food, and the goldfish is in a little bowl, you know, your typical kind of a bowl, and a goldfish is in there, and it grows to the size of the bowl, and so he puts it in a bigger bowl, and it grows the size of that. He puts it in his bathtub, and it grows to the size of that, like that. and he throws it into his big backyard swimming pool, and you have a huge goldfish that grows to the side of that, and that scared me as a little kid, thinking, goodness, what if he would have thrown it in a lake or the ocean? So the thing just kept growing to the size of the container. But the point is, that doesn't actually happen in actuality, right? This amount of mold may grow to the size of the container, but it's not going to fill out and grow to the size of the universe. So apparently this model is not good in the long run. It might be good for the first couple hours or something, but as soon as it starts getting close to the container, all sorts of things happen. It doesn't have enough space, it may not have enough food, it may not have enough water, it may not have enough air, whatever the waste products are for the thing, that starts getting in the way. And so there's all sorts of things that keep it from growing. So we need a better model which takes all that into account. Okay, so we need a model that takes into account the fact that it's in this finite container. And we often use the word carrying capacity to indicate basically what's the maximum amount that container can even contain. It might be a container for mold, it might be a pond if you're talking about fish, it might be the carrying capacity of a pasture if you're talking about animals, or maybe of a certain woods, a certain ecosystem. Okay, but it's going to have a certain carrying capacity depending on how big it is and how rich it is with nutrients and things like that. So let's let C be the carrying capacity. Okay, that's the maximum number of individuals that it will hold. Okay, so if you have fewer than that, it could grow more. If you put in more than C, it'll die out because you've overloaded it, okay, and it'll die out. So that's your carrying capacity. So once we have that, and we're still going to let y of t be the number or the amount of, or I'll just say population at time t. Then the question is, how can we get a better model for the growth given the fact that we have this carrying capacity? So if you think about it, there's a couple of things going on. First of all, if the population is very small compared to the carrying capacity, then it's just going to grow exponentially. Okay, then it doesn't even realize that it's in this finite environment, and it's going to just grow. So we want something to indicate that this thing is just going to grow as before, and I'm just going to put a ky there to indicate that you've got this exponential growth, the same as we had before. Okay, it just grows proportional to how much is there. But as soon as you start getting close to C, then we want it to start slowing down. So how about multiplying it by something like this? Look at what this does. When y is very small, then this thing here is basically negligible, and you just got roughly a constant times y. And if you have a constant times y, then you know you're going to get growth that just looks like that. Just your general exponential growth. But as the value of as the population gets close to C, then notice that this is going to get smaller, right? It's going to go to 0. And as this goes to 0, the amount of growth is going to be less. Agreed? That's what this is saying. The growth is equal to this thing right here, and so if this thing gets closer to 0, that means that the amount of growth gets closer to 0. That's really what we're after, isn't it? As you get closer and closer to the carrying capacity, we want the amount of growth to become less and less. And so that's exactly, and we're going to spend more time on this in the next section, but this is what the thing actually is going to look like, which I'll show you at the end of this section, in fact. If this is C right here, that here's what's going to happen. I'm kind of giving you this a little ahead of time, but it's gonna just slow down, and it's going to get closer and closer to C, and it'll never quite hit there, because as you get closer and closer to C, this gets closer and closer to 0, and that means that the slope is getting closer and closer to 0, so it just levels off. Okay, so there's your carrying capacity. Notice something else that's important. If you start with a population which is greater than C, then Y is greater than C, so then this will be negative. See that? This will be negative. This is still positive. Positive times negative is negative, and that tells you that the derivative is negative, and if the derivative is negative, that means you're decreasing. That's what we want as well. Agreed? That's what we want. We want to be kind of zeroing in on that carrying capacity. If you start with smaller amount, it's going to go up to it. If you start with greater, it's going to go down to it. So there's your equation, which is a very standard equation whenever you're just talking about the population of a simple object, a simple animal rather, in a niche, in an environment that has a carrying capacity, much more realistic than the previous one. Okay, for reasons that we just talked about. So anyway, so there's the differential equation. Notice that it is first order. Notice that it is not linear, just for the sake of noticing, because you're going to get y times y is y squared. So y squared is as soon as you do anything with the y at all, it's not linear. So it's not linear. Notice that it is separable though. It's separable because I can bring all the y's over here and I can bring the dt over here, and notice what we get. We're going to get dy divided by y times, I'll write it as c minus y over here, and I'll leave the k right there, and I'll bring the dt over, k dt, and you can integrate both sides, and you can solve for it. See that? So there it is right there. Now, in the book, and remember, if you don't have the book handy, you can just write and ask me for it, and I'll send you a copy of it, PDF of it. But in the book, I go through all the steps to actually solve this differential equation here, and let's kind of go through them and see how it works. Okay? So here's the first thing we're going to do. First thing we have to do is to do our partial fractions thing here. So I've got a small amount of board space, so let's just do it over here. I have 1 over y times c minus y. And so I'm going to write this as a over, I'll do it the same way I do it in the book, a over y plus b over c minus y. Okay, write it as the sum of those two things. Now we have to find what a and b are. So remember how we do it? We multiply through by this denominator. We're going to get 1 is equal to a. These y's are going to cancel, and we're going to get c minus y, and then b, and now those cancel, and we're going to get b times y. So we're going to get that. So now we need to find a and b. So easiest way to do it is, first of all, let's let y be equal to 0. If y is equal to 0, then we're going to get 1 over here is equal to a, and y is equal to 0, a times c, which tells me that a is equal to 1 over c. Agreed? A is equal to 1 over c. So that thing is just going to become 1 over c right there. Okay? Notice the difference between these constants. C is the carrying capacity, so that's some number that's part of our problem. A and B, these are just constants that we have to find. So C, that's set, but A, that becomes 1 over C. Now, how about B? How do we find that? Let's let y be equal to c. If we do that, then this one goes away. We're going to get 1. Y is equal to c, so that all becomes 0. Y is equal to c, so you're going to get plus bc. And so lo and behold, it tells us that b is also equal to 1 over c. That was easy enough. There it is, right there. Okay, see that? So right here, let's now that we have that, I'm going to get rid of this. Apologize for this. I guess you have it on video. So now I'm going to just write 1 over c in there for both of those things. Like that. And so, if I want to get the antiderivative of that, that's just going to be the antiderivative of this. Okay. So what do we get? What do we get here? Notice that the 1 over c, I want to make sure that I'm still being videotaped here. Hold on a second. Okay, very good. Okay, so I can bring the 1 over c, that's a constant. I can bring that out front. And I can break this up into two integrals, 1 over y dy plus 1 over c minus y dy. Agreed? This one here is just going to be the ln of the absolute value of y. And this one right here, okay, now this is where I'm just going to start leaving little pieces for you to do on your own. So one way, if you don't see how to do this, is to make a u substitution. Let u be equal to c minus y, and then du is going to be -1 dy, and you can go through the steps, okay? You can go through the steps. Here's a little faster way to do it. I just noticed that the derivative of the bottom is almost on top. The derivative of the bottom, c is a constant, so the derivative of the bottom is just going to be -1. So I'm going to put a -1 on top, and in order to keep everything the same, I'll put a negative right there, so I've kept it the same. And now that I have the derivative of the bottom is on the top, I know that the antiderivative of this is just the logarithm of the bottom, because I can just let that be u, and there's your du right there. So this is going to be a minus the ln of c minus y right there. And this is all times 1 over c right there. Okay? And finally, that's equal to 1 over c. Here's a property of the ln times the ln of y divided by c minus y. Okay? That's one of the properties of the ln that we talked about the other day. So all of this can go right there. 1 over c times the ln of the absolute value of y divided by c minus y. Okay? That's all there. Of course, this side is the easy one. That's just going to be kt plus, oh, well, I'm using c for carrying capacity, so I don't want to use c for the constant here. What did I use in the book? Anything? Oh, I used a small c. Well, okay. I'll do the same thing as I did in the book. I'll just make that a little small c there. Doggone it, that probably... I'll make this a very clear big C right there. So that's the big C. Okay? So, boy, you have 23 letters to choose from. You think you'd have enough, but some letters end up being used for kind of the same things. Okay, so now there's our... Okay? And so now we multiply through by the capital C and get what? CKT plus capital C small c. And then what? We take take e to both sides. And so when we take e to both sides, e to the ln of anything is just that thing. And then you take e to this side, and you're going to get e to this, plus that, and then you can use the property of exponents and write it as e to the cc, like that. And then if you get rid of the absolute values, then this will become either the positive or the negative. So, like that. And then this whole thing here, you can just think of as some constant a. So you can just write that as whatever that is. That's going to be some constant. So you can just call it the constant a and put it out there in front. Okay? So now we want to solve this for y. And the easiest way to solve it for y, since this thing is going to be kind of all over the place, this is just kind of a nice little trick in when you have messy formulas like that, is just to call that beta. Let's just call that beta, and it'll help us to solve it for y. And so now we'll have y over this is equal to that, so we'll multiply through by the denominator. Remember now, if we want to solve this for y, we have to somehow get a y all by itself on one side, everything else on the other. And the first thing you have to do is to break all the y's apart. They're connected here by this fraction, so the way to break that fraction apart is to multiply through by the denominator, and you're going to get this like that. Now, of course, it's connected by the parentheses, and so we'll get rid of the parentheses like that. Now everything is broken apart. And now that it is, we want to collect all the things with y in it together. So we can bring this over to the other side. Like that. And then you can factor the y out. And finally, divide through by this, and you're going to get y is equal to beta c over 1 plus beta. And so you have that, and then you can substitute in for what beta is. Beta is equal to this thing right here, and so you're going to get y is equal to a e to the ct times c yet. Oops, I should have had that in front. AC. So there's, see what I'm doing here? Beta is equal to this thing right there. So I have beta times c, so it's going to be a times c, and then here's the rest of it, e to the ckt all over 1 plus beta. And beta, again, is a e to the ckt. So now it's kind of a question of what's the nicest form. You can either leave it like this, or if you want to, you can divide both the top and the bottom by e to the ckt. And if you divide both the top and the bottom by that same thing, you're going to get ac up on top. And on the bottom, you're going to get, you're dividing through by this, so you're going to get an a. And then you're also dividing through by this, so you're going to get plus an e to the negative ckt, capital C. Okay? And I think that's the same thing I've got in the book as well. Yep, there you go. Okay? So, we have all that now. Now, in a lot of these sorts of problems, you not only want the general solution, but you have some sort of a particular solution as well. Let me get rid of this now. In this case, let's suppose that the initial amount of population at time equal to 0, let's just say is equal to y naught. Okay, I'm not asking a question why not. It's y sub little 0 there. We call the y naught, a y naught. So there's your initial amount. So if that's your initial amount, then how does that affect this? In particular, what will A become? C is still the carrying capacity, and K has to do with kind of how fast it's growing, but this constant A is going to be affected by what this initial value is. So how do we solve that? Let's do it over here. So at time equal to 0, we're going to have y naught is equal to y of 0, and if you stick a 0 in here for t, you're going to get what? You're going to get AC up on top, and you're going to get A plus 1 down below. Agree? If t is equal to 0, that's just going to become 1. And so now we can solve for A in terms of y naught. So it's similar to what we just did over here. Again, just a whole lot of algebra. We have to get rid of the denominator. So we're going to write it as A plus 1 times y naught is equal to AC. And again, we're solving it for A, right? So we multiply this through and get A y naught plus y naught is equal to AC. bring everything with the a over to one side. And you're going to get, let me do it the same way as I did here. So bring this over here. You're going to get y naught is equal to ac minus ay naught, which is equal to a times c minus y naught. And finally, a is equal to what? Y naught divided by c minus y naught. So there's your A. So let's put that in here and see what we get. Let's first divide everything here by A. So if we take this thing and divide both the top and the bottom by A, we're going to get C up on top. And this is going to become a 1. And then this is going to become 1 over A times e to the negative CKT. Agreed? And finally, I think this finally agrees with the textbook. We're going to get C up on top, and we're going to get 1 right here. 1 over A, that's the reciprocal of this. So the reciprocal of this is going to be the quantity C minus y naught, all divided by y naught, all times the quantity e to the negative CKT. And I think that's what you have in the textbook as well. There it is. So there's all the mechanics. That's a whole lot of algebra. That's why algebra is the foundation for just about all the mathematics you do in analysis. You have to know how to manipulate things. So there it is right there. So there is the formula for y, for the population. And if you go to Desmus, which is just a wonderful tool for graphing things mathematically, just go to Desmus and go to the graphing calculator there, or I think it's called graphing or whatever, and just put in, it's very self-explanatory if you haven't used it before, and just put in this formula right here. T is your variable, and choose some numbers for C and Y naught that you want. Let the carrying capacity be, I don't care, just let it be 20 or 200, doesn't matter what you want it. And let the initial population be 2, maybe like that. And if Y naught is equal to 2 and C is equal to 20, and let K be equal to 1, just make it an easy number. So K is equal to 1. You should get something like this. It should be some sort of something like that, which starts off as an exponential growth, and then once it gets up to 20, it goes down like that. If you choose your Y naught to be something larger than the carrying capacity, so keep this at 20 and choose your Y naught to be 30, you should see that it goes down like that, just like what we saw before. Okay? So as I say, this is a very important model for populations, and there's lots of other models. We'll be looking at some of them as we go that kind of start with this one, and they if you have maybe various species that are interacting and so on, then this is modified all the more. But this is kind of the standard. I keep saying this. It's the initial one that we started with here. dy dt is equal to ky rather times c minus y. There's your differential equation that models population with carrying capacity. So very good. There you go.